Hi everyone, thank you so much for joining us for a very special guest speaker session today. We have with us uh, Dr. Marlos Machado. I hope I pronounced it correctly. Uh, he's an assistant professor at University of Alberta, and his research interests lie broadly in machine learning, specifically in deep reinforcement learning, representation learning, and continual learning. He's also an Alberta Machine Institute fellow and a Canada SciFar AI chair. Thank you so much for your time, and I'll pass it over to you.
Uh, Thank you very much, Ahmad. Thanks for inviting me to give this talk. I will apologize in advance. I just got a cold, so hopefully there is not too much sneezing in this talk. Uh, but let me start. How do we generally do questions? Like, do people wait until the end to give questions? Do people raise their hands? Just so I know if I need to monitor what's going on.
However, you are comfortable.
Okay, so if people have clarification questions and they want to raise their hand, I'm going to make sure that I'm monitoring what's going on. Okay. So let me start sharing my slides. So hopefully everyone can see what's going on now. So this is a talk about reinforcement learning, and it's a topic that I've given this talk a couple of times already, but it's a topic that I'm very excited about. So I guess I use every excuse to talk again about it. The title of the talk is Representation-Driven Option Discovery and Reinforcement Learning. It is a mouthful, but we are going to parse those terms one by one as I go along. Okay? And again, if you have any clarification questions or something like that, you should feel free. I have a screen on my side, and I can try to monitor it to the best I can to answer your questions. Okay? I won't be able to read the chat, though, so you will have to raise your hand or shout. But yeah, let me start. So as I said, the first thing to notice, of course, is that this talk is about reinforcement learning. In case you're not familiar with the idea of reinforcement learning, is a paradigm of machine learning where we have agents interact with the world, and we learn by trying things out. I would argue that this is actually the most natural learning system, learning paradigm that we have, because it's very similar to what we humans, animals do, and so on, which is just that we learn by trying things out and seeing what feels good and what feels bad, you know? And the idea here is that we're going to have the way that this interaction goes is that we're going to have this agent that is the thing that we're programming, and the agent is going to take actions in the world, and then the actions have consequences. That the agent is going to receive observations of the state of the world. And another thing that the agent receives is a reward signal. And this reward signal is our way of telling the agent what we want it to do. It's a goal, you know? And basically when the agent does the right thing, we give it a positive reward. And when the agent doesn't, we don't. And this is very similar to how we train dogs, for example. You know, like you want to teach a dog how to sit. Every time that the dog sits, you reinforce that behavior, give them a treat or something like that, and then it works, you know? So this has deep roots in animal learning and stuff like that. So to be a little bit more precise, because I'm going to use some of those variables in this talk, the agent is going to take actions AT in the environment, and the environment is going to respond with a state ST and a reward RT. Okay, that's the thing that I already described. And the goal of the agent is to maximize this discounted sum of rewards. This gamma is a value between 0 and 1. And the idea here is that you want the agent to accumulate as much reward as possible. Okay? And we want it to, all things being equal, you'd rather have reward quicker than later. And a concept that we're going to use a lot here is this notion of a value of state, which defines how good a state is. And it's nothing more but than how much reward do I expect to get from this state when I'm acting according to a specific policy pi that specifies how I'm going to behave. Okay, so that's the notation, that's the standard paradigm. And one thing that we have to realize is that this can be, in a sense, quite limiting. Because if you notice here, we're indexing by the state itself. So this is, if you have many states, imagine all the frames of a video game or something like that, then you would end up with many, many states. And of course, we want to have the ability to generalize across them. We want to be able to do well with fewer resources. So what we generally do is this notion of function approximation. And what we do is that we're going to learn this, for example, this function v here, that is going to be parameterized by some weights data. And it's going to approximate the true value of pi, v pi. And of course, at this point, I assume most of you have heard about this. This is that the deep reinforcement learning comes from this very basic principle, which is the idea of using a neural network to parameterize this function v, okay? But in case you haven't been paying attention to RL, in case you think RL is just for video games, as quite often I hear people say this, well, there has been way more than that. RL has been very successful in video games at the beginning, but also we have RL being used, for example, to navigate balloons in the stratosphere, which is a project that I was involved on, to control the plasma inside the nuclear fusion reactor, and many other things that are real-world problems. So in case you haven't been keeping tabs, RL has been quite effective, and this slide by now is also out of date. But of course, it's not that we're done, right? It's not that everything that we do, it's not that RL is done and we can solve any problems. And I would say that one of the problems that we still struggle with is this problem of temporal abstraction. And let me tell you what it is. So basically what happens is that if you think about, we generally formulate things as an MDP, where I'm in a state, I take an action, I go to the next state, I take another action, and so on. But then let's say that I ask you, how do I go to my favorite restaurant? You're not going to tell me, raise from the chair, take a step forward, turn, rotate 30 degrees, take another step forward. That's not how we do it, right? What we say is just like, get ready to leave the house. Call an Uber. Go to the restaurant. So you see that like these different actions have different lengths in a sense, and they are abstract in time. It's a sequence of actions. And this would be a much more natural formalism for us to do it, to deal with RL. But we rarely do that, and we do have a way of leveraging the reinforcement learning paradigm to do this temporal abstraction, these extended courses of actions. And that's called options, like that would allow us to have this extended course of actions, but using the same formalism that we use for RL. And an option is the initiation set, which is like, if I'm going to think about call an Uber, what are the places that I can be that I can call an Uber, the policy is how I would actually act, and the termination condition is like when I'm done with that option, okay? So this is a very, this sounds complicated, but intuitively, it's a very natural formalism, right? Which is this idea of just having extended courses of actions where we can interact with the world. And this is not aspirational. This has many use cases, One of them, of course, is faster credit assignment or planning. Because if I know that I want to go from one place to another, but I know that there's these key places that I go through, it's much easier to propagate credit back when we have these temporal abstractions. It's much easier for me to know that I'm late because my son threw a tantrum than necessarily to say that, oh, I'm late because of the last muscle twitch, the muscle twitch that I gave 30 seconds ago, right? It can also be effective for exploration because you have this temporally extended behavior, so you're not going to be dithering back and forth to visit this, to interact with the world, but you're going to have quote unquote a purpose. It can also be used for transfer. If I get this skill, which is, I don't know, get a key and open a door, this is going to be used across many environments. Many tasks. And again, it's kind of nice to show this, and we come and say, oh, look, there is all these potential use cases and so on. But in this day and age where people really care about applications in machine learning, people will always ask, like, but does this really work? And it does. Like when we were, for example, navigating balloons in the stratosphere, what we wanted to do was to make sure that we had this balloon here being above this region of the space. And we were using reinforcement learning. The way that we did our exploration was to actually use options. Was instead of the balloon saying that, you know what, I will go up a little bit in an epsilon greedy step. what the balloon would do is like, you know what, I'm in the altitude 15 and I want kilometers and I want to go to the altitude 17 kilometers. So the balloon would go up consistently for 2 kilometers to explore that region. And then maybe when it's at 17 kilometers, it comes and say, you know what, I want to see what's above 100 meters above me. And then the balloon would just go another 100 meters. But you notice that like the duration of these actions is very different, right? So, and this was one of the key things that allow us to actually succeed and be able to deploy these balloons in the real world when we learned the policy that was doing much more effective exploration, for example. Okay. And the intuition here is the following, right? Like, imagine that you just want to navigate in an environment. And as a side note, I'm going to use this grid worlds for a lot of the visualization, not because the methods that I'm going to talk about here are constrained to grid worlds, but it's just so easy to convey intuitions in a planar graph, you know? So let's say that you're this agent and you want to find this reward that it's +1 here, you know? It's relatively, the way what most people do it at this time is just like, you know what, I'm going to take random walks. And every now and then I will take a random action and eventually stumble upon this +1, you know? And of course this works, but if you actually watch it, it's painful to watch. You can take thousands of steps, even in a simple environment like that, to just stumble upon the goal. But what if instead of saying that, oh, I'll just take random actions every now and then, what if we had the ability to say, I will go from one room to another? You know, when we go to one room to another, then suddenly now your exploration is much easier because you can, in a sense, when you say, oh, you know what, I will go to the top right room, then you have this temporally extended sequence of actions, and now all you have to do is to stumble upon the goal when you're in the right room. You know, so that's the overall intuition. But the question though is that where do the options come from? You know, because what the examples that I gave when I was telling you about the balloons, for example, we told the balloons that a good abstraction was to say, oh, go to this particular altitude or this other one. When I was giving you the example about the rooms, we were talking about, oh, go to this other specific room. But how do the agent, when it's just interacting with the environment, how does the agent that is just interacting with the environment is able to learn these abstractions, learn what makes sense and what doesn't make sense, you know? And this is the problem of option discovery in the title here. So the main focus of this talk is to answer this question: where do these options come from when we're talking about reinforcement learning? And again, maybe you look at this and you think about, oh, this is an oddly specific question. Options are a niche topic inside reinforcement learning. Why should I care? And I would say that this is actually a very fundamental question about intelligence, which is when we interact with the world from our stream of experience, how do we identify abstractions that make sense, that we can leverage? You know, it is a very fundamental question here. So don't be fooled by the jargon is specific to the field, you know. And to talk about where do the options come from, I promise this is the biggest equation in the, is it true? I think so, in this talk. But the point here is that we can define options using the language of general value functions. So you remember that I defined VPI for you before? VPI is how much reward I expect to get, right? And now we're going to generalize this notion and say, well, what if I want to make predictions about anything? How much? What is my prediction summed over time of this particular sensor that I have in my robot or stuff like that? You know. And then the way we're going to do this is that we're going to define the value function, this GVF, general value function, not only with respect to a policy, but we're also going to define it with respect to a cumulant, which is the signal that you are looking for. It doesn't necessarily need to be the reward. To a termination condition, so it doesn't have to wait until the end. You can say like, well, until I bump the wall, how much do I expect to get of the signal? And Z is going to say like, and then when I'm done, do I get a final value? This is the notion of a general value function. And the idea here is that we can use this to define subtasks. So a subtask, the problem that we're defining, would be to maximize the discounted sum of cumulants plus a stopping value. Notice that this is a generalization of, again, just a standard value function. We could say that the cumulant is the reward, and the stopping value is 0, so we're just trying to maximize the discounted sum of rewards. But here we're generalizing this a little bit to talk about how we can maximize the discounted sum of this special signal, and we're going to get a stopping value at the end. Okay, so this is the problem. We can also get the solution, and the solution would be the policy, and when we decide when to stop. Okay, this is the key thing here. But the beauty of this formulation is that when we look at both things here, suddenly discovering options become much simpler, because now we can constrain the space that we're looking for. And what we're going to do is that we're going to define a subtask. And the option is the subtask that is the policy and determination condition that solves that subtask. So it's good because we're constraining the search space of solution methods. And then we can basically say that the option discovery problem is a matter of specifying the subtask. We have to specify what signal we want to maximize and what is the stopping value function. So to give an example, let's say that you want the shortest path to go to a bottleneck state. So in the 4 rooms that I was showing, for example, let's say that you want to go to the doorway, and you care about the shortest path. Then your cumulant could be -1 at each time step. So you want to make sure that the agent wants to be done with it as soon as possible. And the stopping value could be 0 when the agent gets to subgoal states, and -infinity otherwise. Which means that if the agent stops anywhere else but the bottleneck state, the agent is going to suffer a -infinity penalty. So the agent is not going to do this. And the agent is going to learn to go as quickly as possible to the bottleneck state. This is the standard options that people generally talk about. Then we're going to talk about a couple of different ones. But I think that this notation is very powerful, because I would argue that pretty much any option discovery method that was implemented over the last 25 years can, pretty much all of them can be cast into a simple problem of defining the signal to maximize and the stopping value function. And the option is the policy that solves this problem. Okay. So when we ask where should options come from, we can then replace that question, which is what subtasks should we use? And once we define the subtasks, we can then just solve those subtasks and we get the options. And here's the answer. And here's finally the rest of the explanation of the mouthful of a title that I had, which is basically that we're going to have this representation-driven option discovery cycle. We're going to have the agent interacting with the environment. That's the way that we do things. The agent is then going to learn a representation by interacting with that environment. From these representations, the agent will use those representations to pose a subtask that it's a function of the representation and solve that subtask. This leads to options. These options are then going to empower the agent. These are temporally extended behaviors, right? Like these are skills. Think about them as skills that the agent acquires. These skills allow the agent to do things that it couldn't do otherwise. And because of that, the agent, when interact with the environment, again, it will interact with the environment in a different way, which will lead to a different data stream, which then leads to different representation. And we can keep doing this over and over. Okay, that's the intuition behind the rod cycle. And that is what I would argue is the way to go on how we should discover temporal abstractions by interacting with the world. And let me give an intuition here. Let's say that what we want to do is to interact with the environment, and we're just going to do a random walk. So we're going to interact with the environment and collect some samples. Once we do this, we're then going to learn a representation that captures the places that are further away from where I was. If I do this, the boundary of where I visited. When I do this, I can then discover options that take me to the boundary of that region. Once I have options that take me to the boundary of that region, the next time that I do this and I interact with the environment to collect samples, I already have the skill to push much further, and then I can cover a much farther away region of the space than I could before, which then leads to other options and in a potentially infinite cycle. Okay? That's the intuition behind it. And this works, okay? So for example, this is just a toy example that I like to give. This is a pinball task where basically you have a ball and the ball is going to bounce around here. And if you follow a random walk, each one of these dots that I'm showing you here are like one of the positions that the ball has been, you know. Once we do this and we learn a representation that takes us to the boundary where we have been, which is a place, I'm going to be more precise about this in a minute, but it's a place that we know we can go to, but it's hard to get. We learn an option that takes us to this region here, because it's a place that we know we can get to, but it seems hard to get. If we do the cycle again, then just following a random walk, but now empowered by those skills, we're then able to go through this region, and then we can cover a part of the state space that we couldn't otherwise. Now, which again, it's very empowering. It's a very powerful mechanism. So when we go back to this rod cycle, we can actually instantiate each one of those steps instead of making them vague. And I'm going to instantiate each one of them. And the first one that we're going to talk about is the representation. And we're going to use something that is called the successor representation. Okay. The successor representation, it's a representation that was proposed quite some time ago now. But the idea is that we want to consider that states or observations are close in representation space if they're close in time. Notice that this is something that we can have in reinforcement learning because of the nature of the sequential decision-making problems. But we cannot have in things like supervised learning, right? Because the samples are independent. You don't have the idea of things are being close in time. But the intuition is, let's say that you are in point A here. What state is closer to C or B? If you just look from an Euclidean perspective, C is going to be much closer to A than B is, right? Like you're literally 2 tiles away. The problem, though, is, of course, if this is a wall, it's very hard to get to C. You have to go around. And A then suddenly becomes closer to B. And this is what the success representation does. So what this is showing you here is this similarity to the point A, and you see that B, which is behind the wall, is much closer than C. C is very different from A, even though potentially they would be the same, you know? And the way that we define this is going to be the expected number of times that I will visit this state discounted. This is what equation 1 is showing, okay? And just to point out, because we basically are counting now the number of times that given that I start in state S, how many times do I visit state S prime? And this could be all possible states. We then have for each state a vector of size number of states, and then because we have the number of states as well, different states, we end up with a matrix that is the number of states by the number of states. Okay, and this is what's being written here. This is what this matrix looks like. And again, we can write the success representation as a collection of GVFs, where the indicator function, this thing here becomes the cumulant. Gamma is any fixed gamma, but it's shared across all these GVFs. Pi is any policy that you are using as well, and we have a stopping value that it's 0. Okay, so that's the success representation. And this is the basis for that. And it's kind of neat because there is even scientific evidence that something akin to the success representation is encoded in the hippocampus. Okay, or like the success representation is a good explanation for the types of activations that we see of place cells in the hippocampus, to be a little bit more precise. And then what eigenoptions are, because notice, right, we were talking about the representation here. Now let's go to the options. We're going to define eigenoptions. And eigenoptions are going to look at the eigenvectors of the success representation matrix. And the reason we look at the eigenvectors comes from graph theory. And the eigenvectors of this success representation matrix, it's equivalent to something called the graph Laplacian that has a lot of interesting properties that capture diffusion in the environment, that captures the number of independent components or loosely connected components in the environment. And what I'm showing you here is the second largest eigenvector. And what you can see is that it's assigning a very low value to the states in this room. It recognizes that all these states are close because they have similar value. And that all these states are different than these ones because it has a very large value. But the states are similar to themselves. And you can see that you are clearly identifying the 4 rooms by just looking at the second eigenvector, which is extremely powerful. And what eigenoptions do, if you remember the formulation that I presented about general value functions and defining the subtask, what eigenoptions do is that they maximize this intrinsic reward that we're going to call the cumulant. That is the dot product between the eigenvector and the direction that I moved in my environment. You know, here X denotes the features of state ST. And what I mean by that is, let's say that the agent is here. The eigenvector is going from this direction to this direction, right? Like this is the diagonal that this eigenvector is over. If the agent moves towards this diagonal here, the agent is going to be rewarded for it. Because eventually what the agent wants to do is get to the top of this plot here, and in this case is to get to this state here. This is the option that's being depicted here, you know? Once the agent gets there, it stops, it gets no more reward, and we can even define a nice mathematically sound termination condition, which is to say that you will stop when basically you cannot improve anymore because all your neighbors are worse than you are. Okay? So when we go to this rod cycle again, then what we have is this notion that we're going to interact with the world, maybe following a random policy. We're going to learn a representation, which are the eigenvectors of the success representation. We're going to pose the subtask and solve it, which is to navigate towards the directions that these eigenvectors are pointing. This is what gives us eigenoptions that are then going to empower the agent to interact with the world again. But now the agent is able to do things that it couldn't otherwise, which leads to a different data stream, which leads to better representations, and then we can keep going over and over again. Okay, and notice that I'm talking about here about the plural eigenvectors. So it doesn't mean that we necessarily have only one option. We can look at many eigenvectors and just make sure that each eigenvector defines a different option. Okay, and I'm going to give you an example now, but maybe I'll wait a second because it's kind of awkward to give a talk to myself on a screen. And I don't know if people have any questions. I just said a lot of stuff here, so I'll wait. Okay. I see a thumbs up. Thanks for that. So let me give you an example of what's going on. Okay. Let's say that this is the agent interacts with the environment in these 4 rooms, and the numbers that I'm showing you here is the number of times that the state has visited each one of these tiles. Okay, this is a random walk. This agent starts here, and after 100 steps, the agent is reset to this region again. So this is what a random walk did. There is no information here then besides a random walk. But now we can learn the eigenvectors of the success representation that it's induced by this matrix here. And this is what the eigenvectors look like. Okay. Once we look at these eigenvectors, you remember that what we're saying is that I want you to get to the top of the surface. This is what it looks like. The agent wants to, if you follow these arrows here, every arrow is going to take you to this state here, which is this state. Why is the agent wants to go here? It's not because there is a bottleneck. The agent hasn't observed this bottleneck. So this wall could be closed, and the agent would still want to be here. What makes this state interesting is that it's a state that I visited only once in a region that I haven't visited much. So the agent learns this option. The moment that the agent learns this option, the agent can then interact with the environment again. But the agent, look, it had the ability to just get here. Once it went here, it could just take a random walk, and we see that the agent did spend some time here. But the agent was already closer to the doorway. So after a couple of bouncing back and forth here, the agent ended up visiting the second room. Once the agent does that, this is what the eigenvectors look like, and this is what the options look like. So now the agent is either trying to get to this region here or to this region here, because again, a place that we have visited. We have to have visited the place to know that it's possible to get there, but it seems to be hard from the agent's perspective. You know, you do it again, and you do it again, and in 4 iterations of the rod cycle, we are able to actually visit. The 4 rooms in the environment. You know, and what's interesting here is that if you watch the random walk, these episodes are 100 steps long. It's almost unthinkable to say that in 400 steps we would have visited the 4 rooms in the environment, you know, and this just happened because of how this method is defined, you know, and we can actually show, like this is just of course an anecdote, but we can show that we can reduce the expected number of time steps that we would need to visit every state in the environment by 1 order of magnitude when we do this type of stuff. Okay. Yeah, so I just said this, like, so if you were to do this with a random walk, it would take you 27,000 steps, even though it's a 10 by 10 grid. while with a random policy over primitive actions and the covering eigenoptions, we would get 2300. And you also see that it's much more diffused. We're much better off in visiting all these states in the environment. But of course, this is the state that we visit the most because we always start from here. And this is the state that you visit the least because it's the further away. Okay, but it's still much better than what we had before. So after this, like this, as you've seen, as I go along, maybe you'll notice there are many references that I'm using as we go along because we've been developing this type of technique and making it more robust and more reliable over the years. But every time that I would present this talk, there was a laundry list of common complaints. Oh, this talk is only tabular. What about general function approximation, neural networks? You're not learning a representation, so you're not deep. And when they say that I'm not learning representation, of course I am, the eigenvector of success representation, but what people actually mean is that you're not doing deep learning. Does this work beyond grid worlds, navigational tasks? You're not maximizing reward. RL is about reward maximization. And eigendecomposition is expensive. It's so cubed. This is not scalable. What if the environment is not symmetric? You can't assume symmetry. It's an eigendecomposition. You have special phases, and you can't just wait for a long time for a phase to finish so you can go again. The uniform random policy is not a good baseline. You should use X, and X is whatever paper people wrote about this. And the success representation is policy dependent. Are you depending on the random policy to learn the success representation? So like every time I would give a talk, I would have made a lot of money if I just have bet that I would get 2 or 3 of those questions at the end of the talk. You know, like this is the default things that people always say. And I always had an answer for that, but you know, it's hard to convince people. So we wrote a whole paper to show to answer those questions. So remember, we have the rod cycle, but the problem with the rod cycle here, if you think about it, is that every single iteration here, it requires some approximation for us to scale things up. You know, learning a representation. Well, the success representation, as I told you, it's an S by S matrix. So if we have many states or infinite in continuous action space, state space, for example, then of course we can. It doesn't scale. You know. Then to pose a subtask and solve it again. If we're going to do this in complex environments, we have to use some function approximation, and everything that I was showing you so far is tabular. But now we have these skills, then let's say that there are policies with neural networks. How do we actually interact with the world, and so on and so forth, you know. And basically, I guess the most interesting part here is to show you how we can approximate an eigendecomposition using a neural network, you know. We want to learn the eigenvectors of success representation, but instead of learning the matrix and then computing the eigenvectors, we can have a neural network that directly estimates the eigenfunctions of this graph Laplace. So basically what you get is that you get an observation, let's say an Atari image or whatever, and then if you want to say, oh, I want to approximate the top D eigenvectors, you would have D outputs, and it would tell you what is the value that the eigenvector is assigning to that particular observation that you saw, right? Because if you recall from my talk here, each state gets a value assigned to it. So we are learning how to predict, in a sense, the height of that plot with a neural network. And then as we visit, and because the reward is defined in a way that it's just pretty much the gain in height, we only need to have a local information about this. Okay? The objective is kind of cumbersome, but the idea is that we want to make sure that the states that are close in time, that are one adjacent to the other, they are close in the representation, but we also want to make sure that different eigenvectors, J and K, for example, they're orthogonal to each other, and this is guaranteeing the orthogonality. Okay, this comes from a graph drawing objective. There are a couple of details here. I'll talk more about this at the end, but this is the objective that we used. Okay, so then we can do approximations all the way down. We can use a neural network to learn the Laplacian representation. We can then now, if we have the neural network, every time that you observe a state, we receive an observation, we compute the value of that eigenvector, we go to a next observation, we compute the value. The difference between that is what we're going to use for reward. So now we have a well-defined problem And then we're going to do the parallel to learn those policies, okay? And we're then also going to do the parallel to learn how to maximize reward, because this is an RL talk after all, okay? Once we do this, for example, let's start with these grid worlds, but this time it's difficult because it's images, like this is being represented as an image. What we can show is that we can do everything online. All those things happen, all that cycle happening at the same time. We not have the phases anymore. And glue is our method, this deep covering eigenoptions. And what you can see is that you're able to get from the go state, the agent to get to the go state, much faster than a lot of the baselines that people like random network distillation, count-based exploration, easy greedy, or the double DQN here would just be the equivalent of a random walk. Okay. So it works, But more than that, what it's interesting is that, I mean, if I went through all this trouble, right, to show you this method, and then at the end of the day, it works as well as, I don't know, random network distillation, which is pretty simple, this would be pretty underwhelming, right? But what it's interesting is that, imagine now that the world changes. Imagine that there is no stationarity in the world. And I would argue that our world is constantly changing, a lot of those methods about exploration, they have very strong assumptions about, oh, I'm keeping counts of how many times I've been to the state. And if I don't know that the world has changed, I don't know how to reset those counts, right? So what we change is that instead of having the agent having to traverse this diagonal here, now there is this diagonal that the agent needs to go. So the start state and the go state changes. And also some of the walls are blocked off, okay? So what you see is that this is just the first plot compressed. But now when the world changes, every method drops the performance. That's expected. But we recover much quicker. And the intuition here is fairly simple in a sense. When we learn options here, we're learning skills that allow us to navigate in the environment, which is very different than just learning counts of oh, this is what a good state is or a bad state is, So because we have these reusable skills, when the world changes, well, we still have learned something that is useful. Maybe some are not, right? Like maybe the one that goes from here to here through this is blocked off, but there are many others that will be useful. And we can see that this is actually reflected here. But we can do more complicated stuff. Let's say that the agent is here, and now the agent needs to break this wall, to get a key, and then go back and then open a door. By breaking the wall, the agent cannot put the wall back. So now the environment is not even symmetric anymore. And again, if you do this, you see that our method performs really well. And I just want to point out that the only reason that I think counts perform well is because this is actually a cheating baseline, because we're counting state visitation for real and not using pseudo counts or anything like that. So this is even more generous to the baselines than it should have been. Okay. And the thing is that it continues to look promising. I keep showing you this grid world plots just because they are very intuitive. But if you look at Montezuma's Revenge, for example, and I just have the agent interact with the world for a while, and I look at what are the eigenfunctions that we learn of the graph Laplacian. This is the three eigenfunctions. So let's look at the first one. Darker means a low value, and lighter means a high value. And what the agent learns to do is to get the key. But notice that the agent is not trying to maximize reward at this point. They just not even see a positive reward when it collects the key. But again, this is the thing that the agent knows that it can do by chance, that it's still easy to do. That it knows it can do by chance, meaning it's still possible to do, but from the agent's perspective, it's the hardest thing that it can do, right? It is the hardest point for the agent to get to. And it's pretty cool. It just, out of the math and out of the intuition of those methods, we just get to observe that from the data. You just learn that, And of course, this is just the eigenfunctions, but then we can then look at reward maximization curves. And you see that this is in Montezuma's Revenge. We do pretty well within a limited time budget. And then when we also look at things like navigating in this environments here, we also do pretty well with partial observability, and a lot of the other methods, they cannot even get off the ground. Okay. So when we go back to the laundry list of common complaints, I want to say that we addressed every single one. Of course, this is not tabular anymore. We are doing deep learning in every step along the way. We are using deep RL to learn representations. Does this work beyond grid worlds and navigational tasks? Yes, like Atari games. We also have experiments in Rubik's Cube and stuff like that in the paper. Now we are maximizing rewards. We are using neural networks to approximate the eigendecomposition, so we're not paying the cubic cost anymore. Our environments were not symmetric, so we're not assuming symmetry. Everything is happening at the same time, so there are no phases. We consider a bunch of baselines that people like random network distillation, diversity is all you need, counts, and so on. And we are just learning the successful representation with respect to our current policies, so also it doesn't really matter what policy we're using. So I think this is very powerful. And I gave this talk a year ago or so, and I was already very excited about this. And since then, my lab has been working on extensions and pushing the boundaries of what we can do with this framework. And I just want to talk about, yes, I basically said how excited I was about this when I tweeted about this paper. But now I want to talk about just one of the things that we have been thinking about to wrap up, which is this notion of, if you remember the objective that I wrote, this is the equivalent objective that I wrote before to learn the eigenfunctions of the graph Laplacian. There are some challenges here, it's impossible to tune the hyperparameters. This for example, this b here, because the way that people have been tuning these hyperparameters is that they would, let's do a grid world, so that I can solve the eigendecomposition in closed form, and then I will train a neural network and I will tune the hyperparameter to see what is the hyperparameter that gives me the value closest to the thing that I know the ground truth. But I would argue that if you know the answer, why are you doing a neural network? If you can compute it without neural networks, why are you using even using neural networks? Of course, here we are not getting eigenvalues, we're just getting eigenvectors. And we can also show that rotations of the eigenvectors are equilibrium points when you're using stochastic gradient descent. So this year we had a paper at ICLR, the augmented Lagrangian Laplacian objective, we call it ALO, that basically it's longer, but the intuitions are still pretty much the same. We still want to keep states close together, but that are close in time, close together, but we have this augmented Lagrangian thing that it adds this extra term here. And we have stop gradients, but basically, despite being very complicated, it doesn't have any hyperparameters for us to tune. We get the eigenvectors back out of this optimization. They show up here in the betas, and we can prove that the rotations of the eigenvector are not equilibrium points, even when using SGD and neural networks. And the intuition is fairly simple. It's because of the stop gradient. So I cannot have eigenvector here, and I want to learn an orthogonal eigenvector. And in the objective above, if I rotated one, the other one could just follow along. But now, because I'm keeping one fixed, as I rotate the other one, this doesn't move, and it works. Again, this is just showing you how robust, this is what the hyperparameters, that the impact of hyperparameters in the previous methods, and this is ours. So basically, you can pick any hyperparameter and we are still going to converge. A bad hyperparameter is just going to ensure that it takes longer for you to find the right answer. Also, it's not only more robust, but it's more accurate than what we had before. It works across different data streams. We have results with images, with XY coordinates and stuff like that. And in the paper, we have shown that all these three coefficients, all the three components in that loss function matters. So it's kind of neat. And this, again, empowers us to do much more, right? So one of the things that we're looking now is just what if we start following the rod cycle, but with ALO now, instead of using this GGDO, how well we can do. There are many other things that my lab has been looking at in terms of how we can leverage options to do better reinforcement learning. Okay. So to wrap up, I'm personally very excited about this, because I think for the first time, and this is a big deal, but I think that honestly, I think it's for the first time we have an option discovery method that is general, that works, and that we can demonstrate a virtuous cycle of improvement with it. It's fully experiential. There is no data set collection. There is nothing. It's just based on the experience of the agent. It is scalable. It is amenable to function approximation. It works for different data streams. It's not contrived to find bottlenecks. It's not contrived to find a specific type of particular state. It works in any environment. The ideas are applicable to any environment. It doesn't make assumptions about the topology of the environment, so there's no domain knowledge being added here. It's just looking at the eigenvectors of this graph Laplacian success representation. And if you want to be cheesy about it, I would say that it's sort of biological plausible if you're into that kind of thing, in the sense that we're using a lot of the ideas that now have been associated with things that are used to model activations in the brain, such as the success representation that explains a lot of the activations that we see of place cells in the hippocampus. But also, if you look at the activations of grid cells in the entorhinal cortex, guess what is a good explanation for it? The eigenvectors of success representation. So there is a lot of things that are related in that aspect as well, which I think it's pretty cool, you know. So I believe that temporal abstraction should be a central piece of reinforcement learning. It's kind of weird to think about sequential decision-making problems without this ability to abstract actions over time. But there's this question that always lingered. Where should options come from? Or if you want to be bolder, what is the origin of abstractions? And what I propose is that specific representations learned by the agent are the answer, you know? And given the right discovery method, options are easily scalable. And I show some of the results here. My lab is working more on that. But I would say that options are particularly helpful for continual learning in the face of non-stationarity, when the world is changing, but you want to be able to have skills that are reusable, you know? So maybe the take-home message here, and it's something that I really believe, quite often I write in my grants, is the fact that state representations and temporal abstraction should be deeply intertwined, where representations and options are constantly refined based on each other. And hopefully this cycle that I presented today and the results have at least made you curious about this type of approach and this perspective over how to do sequential decision-making in right now, okay? So I just want to thank the collaborators. These are all the people who are co-authors of the papers that I cited along this talk. Many of them are my students. I guess here in this talk, like we have, for example, Fan, who did the animations, Martin Klisarov, who did the scaling up Eigenoptions. There is Diego Gomez, who was, for example, the guy who did the ALO thing, you know. And I'll stop here. I haven't been monitoring the chat, so I don't know if there are questions, but thank you so much for your attention. And I'll take questions now. Any questions? Should I open the chat? There's some conversation here. AI, hi, AI assistant again, another AI assistant, a lot of AI assistants. There are a couple of questions that I don't have the context anymore, like are you summing over K, how it calculate? Reginald is asking this question, like, is the intrinsic reward produced similar to the state coverage methods of diversity is all you need? So, well, there is some there is some similarity to some extent, but because how do I answer this? So there is some similarity to some extent, but I think that these other objectives, they are much more forceful, like, oh, I want to maximize the entropy of state visitation and stuff like that, which is very specific. And here, this diversity is not directly encoded. Instead, it is generated by the fact that we're looking at eigenvectors of the success representation. So the way this works in a sense is to say that instead of explicitly telling the agent, oh, I want you to maximize the entropy of state visitation or something like that, what we tell the agent is like, look, you should act according to the eigenvectors. The eigenvectors, by definition, because they were talking about each other, they are covering different parts of the state space. So you could get that. But it is tricky because, like, if you look at this thing, for example, here, right? Like, if you look at this plot, what I presented today were this notion of eigenoptions that we would go from this state to this state, and we're good. But now, nothing prevents us from using exactly the same eigenvectors to do a mean cut here. And we identify the bottlenecks. And then we could use those to do planning, for example. And actually, if I recall correctly, Osgur Chimchak has a paper that's very similar to that from a long time ago that did this, but it was not about exploration. So the framework that I'm presenting here, it's much broader than necessarily thinking about exploration, but because I use that as a use case here, it just made sense. But it's not necessarily that we only want to do the diversity. We're definitely not encoding that explicitly as the loss function, if that makes sense. Cool, I think it makes sense. Any other questions? Okay, Karam, go ahead.
Thanks for your presentation. Actually, I would like to learn more about this if I want to, in my time. So, where can I find the resources to read for this?
Yeah, everyone should absolutely learn a lot about this. So I would say that this paper here, Machado, Barreto, Precup, and Bowling from GMLR of last year, I would say that this is a great reference for you to start. It is a very long paper. I admit that. It has 70 pages.
Okay.
But this is in part why it's a good reference, because instead of trying to rush things through and assuming that you have the background in a conference paper, I actually wanted to write this long paper to set up the ideas and have time to do it slowly, so in a sense, this paper here, it does everything just in the tabular case. For example, it's where the example that I provided is in a way that sorry, you're seeing all my backup slides in a sense that oh boy, I have backup slides. In a sense that you can get the intuitions, you can get the results, you can get the visualization without being bogged down by more complicated approximation stuff. And then once you get the intuition of this 2023 GMLR paper, then it depends where you want to go with that. One of the papers that it's good is the ICML paper that I wrote about this scaling up things with Martin Klisarov last year. But maybe you were interested in how we learn the eigenvectors of the Laplacian neural network. So that would be the ICLEAR paper that Diego Gomes wrote this year. Or honestly, even Diego Gomes' master thesis, which is pretty good in terms of explaining the lay of the land for that type of method. But overall, I would start with my GMLR paper from last year because it's a pretty good introduction to the topic.
Sounds good.
Cool, thank you. Okay, I see a question from Vladimir here. When environment changes and your model still learns better than other baselines, is that because of reusability of previous learned representations, just because your method is generally better in fast learning than others? Well, this is a great question, and it's a really difficult question to answer, because one thing that you have to realize here, and I didn't mention this, but it was on purpose, is that we have neural networks, different neural networks to learn each option, and even a different neural network to learn the Q function. And the reason that we did this was that we wanted to disentangle potential benefits of saying oh, maybe it's because you have an auxiliary task effect, and then you're learning representations that are better, and so on. And no, that's not the case, because this is not being touched by the Laplace or anything like that. But when you say that a method is better in fast learning, well, if you have better data, if you're doing, for example, better exploration, right, you will learn faster. So do we get better exploration because of the reusability of the options? That's the only source of exploration that we have in this method. So at least right now, it's not necessarily clear that it's easy to disentangle this, why a method learn faster. We're using the same learning algorithm as underlying all of these methods, either double DQN or rainbow. So It's not that you have a better algorithm than other. We don't have auxiliary task effects because we are not sharing the parameters of the neural network. So I would say that it's because we're doing better exploration, and then the reusability part is just a natural consequence of how these methods work. I'm sorry, at the moment that I start answering questions, I start looking at my laptop that it's here, so then I stop looking from the screen. Any other questions, comments, feelings, complaints that I can add to my laundry list, so then we can write another paper?
Yeah, so I had a comment here with respect to the hierarchical reinforcement learning. So how does that relate to the kind of the grid world representation paper that you had earlier?
So hierarchical reinforcement learning is a word, it's a term that broadly encompasses a lot of the things that are dealing with temporal abstractions, right? Options are an example of hierarchical reinforcement learning. Probably the main example, the most famous formulation of temporal abstraction. But in a sense, you could think about hierarchical reinforcement learning without using options. For example, feudal methods, feudal reinforcement learning, for example. But in general, options are just one way of doing hierarchical reinforcement learning. Any other questions? Okay, then maybe that's a wrap.
Yeah, I guess we can conclude the session here. Thank you so much for your time.
Thank you so much for the invitation again. And thanks everyone to show up and ask questions. I really enjoyed this.
Thank you. Take care. Bye.
Thanks.
Thank you very
Take care.
much.